Okay, so you see these incredible robots everywhere in the news, right? They're flipping, they're running, they're doing tasks that honestly look like something straight out of a sci-fi movie. It really feels like the future is here, like right now. But behind every single one of those amazing machines is this hidden challenge, this massive hurdle that engineers have to get over before a robot can even touch the real world.
So to really get a handle on that hidden challenge, let's first take a look at what's getting everyone so hyped up. I mean, the most recent Consumer Electronics Show was the perfect showcase, just buzzing with technology that felt like it was pulled from a Hollywood set.
And you know, it makes you ask the question, is this finally it? After decades of promises, are we actually at the dawn of the robot revolution? All the media hype certainly makes it feel that way.
At CES 2026, there was this new buzzword flying around everywhere, physical AI. See, for years, the focus has been on the software brains, like ChatGPT. But now, the tech world is obsessed with giving that intelligence a body. We're talking about AI you can actually see and touch, everything from cars that drive themselves to humanoid assistants in our factories. I mean, the showroom floors were just packed with these physical AIs. We saw way more advanced self-driving cars, humanoid robots built for factory jobs, little robotic companions, even wearable exoskeletons that give you a strength boost, and smart home gadgets that can climb your stairs. The future feels like it's just right around the corner. Okay, but here's the catch. Behind all of that incredible futuristic hardware is the single biggest challenge holding this all back. It's this huge problem that literally every robotics engineer is wrestling with, and it's called the reality gap. So, what exactly is it? Well, the reality gap is the difference between the perfect, clean, digital world where these robots are trained and our messy, unpredictable physical world. Think about it, right? Robots learn by practicing a task millions, even billions of times inside a computer simulation. But that simulation, it's just an approximation of reality. It's not the real deal. And this, wow, this is the perfect illustration of that gap. On the left, you see the robot as it exists in its training simulation. It's simple, it's clean, totally predictable. And on the right, that's the actual robot. Just look at all the extra complexity, the wires, the textures. The real world is just, well, it's a lot messier.
Here's another great one, with a robotic hand solving a Rubik's Cube. The digital version on the left lives in a world of perfect physics, flawless movement. But the real one on the right, it has to deal with tiny imperfections, with friction, with all the intricate wiring that actually makes it work. That difference, that's the gap.
So what's actually causing this gap? I mean, why can't we just build a perfect simulation? Well, it turns out reality is just infinitely more complex than even our most powerful computers can possibly model.
And look, the stakes here are incredibly high. As this research paper points out, a robot that does something perfectly in a simulation might just be exploiting some flaw in that digital world. So when you try to transfer that behavior to a real robot, it's not just that it might fail, it can be downright dangerous.
Now this slide is really interesting because it shows you how they simplify things. On the left, that's the physical robot setup. On the right, that's its digital twin, the version they use for simulation. See how it's basically a wireframe? It's missing countless real-world details, like the exact texture of a surface, the tension in the cables, or even tiny vibrations. Let's just break it down a bit. In a simulation, all the parts are perfectly rigid, but in reality, things bend and vibrate. A simulation has these ideal friction models. Reality has complex friction that changes with temperature and wear. In a simulation, sensors are perfect. In reality, they have noise and delays. And honestly, the list just goes on and on.
So, if a perfect simulation is impossible, then how in the world do we get these robots to actually work? Let's get into the solutions and see how researchers are tackling this incredible challenge head-on.
Well, it's not some magic bullet. It's actually this really methodical process, kind of a recipe. Researchers build the best simulation they can, and then they specifically design training methods to make the AI tough enough to handle the differences. They train it, test it in the real world, see what went wrong, and then they go back, tweak the simulation, and train it all over again. It's this constant cycle of refinement.
And one of the coolest, most powerful tricks they use is something called domain randomization. Instead of training the AI in just one perfect virtual world, they train it in thousands of slightly different ones, all at the same time. So one simulation might have higher gravity, another might have slippery floors, a third might have flickering lights. By learning to succeed in all of these weird, chaotic conditions, the AI becomes robust enough to handle the one true reality.
And when these techniques work, something truly magical happens.
That digital dream crosses the reality gap, and it becomes a physical reality.
You gotta check this out. On the left, an AI learns to fly a racing drone in a simulation, zipping through virtual gates. Then, on the right, that exact same AI programming is downloaded onto a real drone, and it outperforms world champion human pilots in a real-world race. I mean, that is what sim to real success looks like. It's incredible.
And look, here it is again. A two-legged robot learns to handle stairs in a totally digital space. It can fall down and get back up millions of times without ever breaking a single expensive part. That virtual practice is what gives it the skill to then successfully walk up a real step in a physical lab. So when you boil it all down, what this really means is that every amazing robot we saw at the beginning, the humanoids, the self-driving cars, all of it, they're all the direct result of scientists and engineers finding brilliant new ways to bridge this fundamental gap between the simulated world and our world.
So the next time you see a robot doing some complex task out in the wild, you'll see more than just a piece of hardware. You'll see this whole invisible journey it took, the millions of virtual failures, the thousands of randomized worlds, and the incredible leap it had to make across the reality gap just to get here.